Okay, so in this video, I just wanted to carry on a bit more on graph theory. Not graph theory, group theory. So we've kind of looked at the basic properties of groups. So, what makes a group? So let's have a look at an example and recap. So this is called the trivial group. So let's confirm that it is a group. So this is an identity element. So we have that this group, let's call it G, has an identity element. It's basically the only thing in the group. And clearly, every element has an inverse because the identity is its own inverse. So we have an identity. We have an inverse for every element. Is it closed? Oh yeah. So we just have to check whether the identity times the identity is identity and is by definition, so it's closed. And one more, associativity. And it's not hard to show that this would just be E star E, and then this would just become E star. Oh, sorry. E like this and star. So for this one, even associativity was actually easy to prove. Okay, so associativity. And so this is a group, and in fact this is called the trivial group. So G equals is the trivial group. Okay, some other forms of groups include this is called the cyclic group. Generated by G. So this is equal to the set G to the n such that n is a natural number. Now this group need not be infinite. For example, if G was -1 and this was the group, it was a group under multiplication, then this set would just have -1 and 1, right? And so in this case we would say that the that -1 in this group this would actually be a group, if you notice, because it's closed. It's closed. -1 times -1 is 1, which is in the group, and we have that, we have this, right? So we have inverses. There is own inverse, if you notice, and yeah, so this is a group. Well, associativity is because of associativity multiplication. So it's a group, and so and we have an essentially cyclic group generated by -1, and there's a group under multiplication. And we have something called the order. So the order of -1 in this group is the cardinality of the cyclic group generated by -1. So it would be 2 basically. And so similarly, you can see the order of 1 in that group would be 1. Okay. we kind of have an idea of what a cyclic group is now, and let's have a look at some other groups. So there's the dihedral group. Okay. So the dihedral group. Let's try look at the dihedral group. So this is a triangle. Well, obviously, but obviously, you notice that you can do a certain amount of some kind of transformations to the triangle and keep it as it is. For example, you could do a 120-degree rotation, a 240-degree rotation. But then if you try to do like a 360-degree rotation, you'll just get back to the beginning. Okay. Now you can also do a flip. We could flip along this direction, and which would be different from all the others. Which becomes more clear if you label the sides. And over here would be 1, 2, 3 this way. Over here we want to flip in a different direction. We'll flip it this way instead. So 1, 3, 2. Finally, we'll do it like this, which is and this would be 2, 1, 3, like this. Okay, and you'll notice all of these are different. Now you might ask, are there any more symmetries of this right triangle, so symmetries of this equilateral triangle? That means, is there any more ways we can jump around these numbers? So essentially we want to do transformations of this triangle and keep it looking the same. Well, I know my pictures all look different, but essentially you want to like pick up the triangle, somehow flip it or rotate it, some sort of transformation, and then put it back so that it looks basically the same if it weren't labelled. To be fair, that's basically like a physical understanding of it, but essentially what you have, and this is called a dihedral group of D6, dihedral group of order 6, and essentially it's actually composed of 2 different groups. One is a cyclic group of order 3, and then another cyclic group of order 2. And basically they're combined, they're combined, and this would be the trivial group, and they're combined to make D6. Okay. So this would be the identity. This would be rotation. This would be R squared. And this would be a reflection. If I want to call it F for flip, this would be, okay, if you notice, this would be a rotation and then a flip, which is not evident to me at first glance, but it can be shown to be true. Let's see what that would look like. So we want to somehow rotate it and then flip along. So it actually turns out it's R times flip. So you rotate it first. So you rotate it this way, and then you flip it this way, like along like this. And this leftover one would just be R2 and then flip. One question you can ask is this a commutative group? So multiplication is commutative in that A times B is equal to B times A. And maybe at first you might think it is, but let's actually give it a go. Let's see if we can, what happens if we flip and then rotate rather than rotate and then flip. In fact, I should probably write it the other way around. That's how it's normally done, isn't it, in function notation? You would normally write it like this, because you apply this function before you apply this one. So it'd be, and also matrices. Okay, okie dokie. So let's confirm. So let's try to do the flip first. So if we do the flip first, we get here. And now if we rotate, we get this one. So if we do a flip and then a rotation, we get a flip times a rotation squared. So it turns out it's not commutative, it's a bit different. And well, it does turn out that most groups are not commutative, so it shouldn't be a surprise. And actually, yeah. So that's basically what I wanted to say in this video. Yeah, and thanks for watching. So basically in this video we looked at examples of groups. We had a look at what an order of a group was, what a cyclic group is, what a trivial group is, and we showed the trivial group is in fact a group. We didn't show that the cyclic group is a group, but you can see the closure, closure, because it's closed in the binary operation, and we're just taking powers, so just multiplying the powers together, we would add the powers essentially. There is an inverse, because you can just, if we know the order of the group, then g to the n, which is the element of the group, multiplied by g to the order of the group minus n. This would give you the identity element, so that way you can find inverses and they're unique, because since this is unique, as long as it ends, ends less than the order of the group, and obviously bigger than 0. In fact, if we want the identity bit in there, we'll just let it be 0 too. There we go. And what else? Associativity comes from the associativity of multiplication. This actually turns out to be a commutative group. It's called an abelian group, because commutative is sometimes hard to say, I guess. I think what else? Yeah, I think that's it. Okay, so thanks for watching, and see you next time.